Miss Forchibe, Ethelyn. She is an agric, entomologist, and entrepreneur from Cameroon, passionate about revolutionizing the agric sector across the continent through holistic pest management approaches. With an academic pedigree in zoology, that was a BS in 2013. She also has an entomology MPhil in 2016. And she went on further to proceed with a PhD. And then she has got so much capabilities. We're working with vegetable farmers and all that. And then she'll be co-presenting on using machine learning on remote sensing data to identify the distribution of and density of aphids on cabbage. She'll be doing this with Mr. Isaac Newton Kisiedu, who has a geometric engineering background and has worked in a variety of industries. He's a geospatial expert with more than 5 years of hands-on experience in GIS, remote sensing, software development, database management. And then he has been in the industry for quite a number of time now, for like 5 years, more than 5 years. And then I personally know Newton, and then he's very good with Python and everything programming languages. And so I am happy that both of them will be presenting on using machine learning or remote sensing data to identify the distribution of and density on aphids on cabbage. So we'll start with Ethelyn, and then Newton will join me. So ladies and gentlemen, let's welcome Ethelyn as she takes us onto the application of remote sensing. Thank you.
All right, thank you very much. Generally, insects, as we saw in the earlier presentation, as Rose told us about using remote sensing data, for pests. What if you're dealing with insects that are very small? So insects, for example, move from one place to another based on the activities of man, particularly trade. Because, for example, some insects are not endemic to certain areas, but then you find them in particular places. And cabbage, for example, is not a Ghanaian vegetable, it's a Mediterranean vegetable. So for it to be in Ghana and then you have this pest and accompany them, then it's to tell you that it came along, due to movement of different vegetables or trade and all of that. So recently in Ghana, there's been a high, growth in the production of cabbage, mostly in the peri-urban areas and the urban areas, because cabbage is mostly consumed in the urban areas. But at the same time, it also serves as a source of income for the rural farmers that do grow them. But over time, they faced a lot of constraints due to pests, due to sometimes not getting adequate land to farm this particular vegetable. But we've realized that infestation by aphids is a major constraint because from the plants, killing the plants, they also transmit viruses to these plants, which ends up killing them. And so if you have, say, for example, a viral infection in one farm, you could have the whole farm going down in just a couple of weeks. And on the picture right here, I want you to just see how tiny they really are, but then they can cause quite a lot of damage to the crops. So recently, we identified two major aphids on cabbage. We have the Lycophis erycimi sodobrassicae and the Myzus persicae. So for ease of communication, I'm going to use for the Myzus persicae. So we can see that when the pictures here are just pictures of the viral disease that they transmit. And once they do transmit these viral diseases, give it a couple of weeks and you have all these plants down. So we wanted to look at different ways to be able to map these particular insects. So it doesn't take us too long to have to move from one farm to another, before knowing how widespread this insect is in Ghana, especially the Lycophis sodobrassicae, because it was just recently reported in the country. So now I want to understand, why are we using spatial analysis for this pest? I mean, we've seen in earlier presentations the usefulness of remote sensing, in different aspects, from natural resource management to agriculture. But in this presentation, we'll be looking at it particularly for this pest, aphids, on cabbage. So over the years, we've had a lot of researchers kind of reporting the use of remote sensing data in entomological research at a distance or without even destroying the plants, and be able to respond to whatever damages they are causing. And also to be able to understand how these insects interact with ambient conditions such as environmental factors. So we'll be able to, tailor our management practices, towards this understanding. So remote sensing data is very powerful when it comes to precision agriculture. And so, as earlier mentioned, it helps us to understand the correlations and the spatial links between insects, their presence, their absence in a relationship to climatic factors, environmental factors, and also human factors. And once we do understand this, then it's going to guide us in control methods, management methods, and also resource allocation for making sure that we improve on agriculture. And so to understand this for this particular aphids, we did sampling for this particular species in the major cabbage producing regions in Ghana. The next slide is going to show us a map for the different regions that we actually sampled. And so we sampled from 20 plants in each farm and collected the colors. As we saw in the earlier pictures, we had the green ones for the LEP, and then we had the pink ones for the Myzus persicale. So we took them back and then confirmed the identification. And we used a GIS device to record the presence locations. We also counted the number of aphids for each sampling location so that we could use it subsequently for the spatial analysis. So here, this is the map that shows the different sites that we visited. So in total, we visited over 91 sites, and 89 of these sites, we found the Lycophis erysimis odobracicae, and then in 76 of these sites, we found the Myzus persicale. But in total, we had both insects co-occurring in 74 sites, suggesting that whatever factors, that kind of favors their establishment, their biology, their growth and reproduction, is kind of the same for both insects. So we sought out to understand this by using remote sensing data. And so Newton is going to, go ahead with the presentation and show us how we did this and whatever results we got. Thank you. So I'll let Newton continue with the presentation.
Thank you very much. So basically, Ethelyn has already set the ball rolling, and I'll jump right into the spatial analysis part of this research. Basically, in spatial distribution studies or analysis, we are kind of interested in where these species are located. And what that means is that in spatial science, when we see points on a map, we want to try to understand whether, okay, at these points, what is the distribution behind these points? And if we realize that, okay, this phenomena is occurring at random, then we are not really interested, or we are not so curious about why they are random. But if we realize that the points are occurring as in they are clustering at a particular point, then that raises a lot of questions to say, okay, so what is the underlying factors that are causing these points or these phenomena to cluster at this location? So basically, 3 basic questions were raised, and these are the questions that are going to drive the spatial analysis. And the second question was that in case form of distribution, which is not random, then what could be the underlying contributing factors that are causing these insects to, group together at a particular site? And then the last question that would drive this analysis is to look at, once we understand the contributing factors, then what will be the suitability of these contributing factors affecting where we are expecting to find these insects. So without wasting time, I would move on to the next slide, which is addressing the question 1, which is looking at what the spatial pattern or the spatial distribution is for these points. So I did average nearest neighbor analysis, and this is basically trying to understand the spatial distribution And what that means is that it's average nearest neighbor analysis computes the average distances between all of the points you saw on the map, and then it compares that to that of a random distribution. So once it does that comparison, and then it finds out that, okay, the observed average nearest neighbor distances are less than that of the random distribution, then we can conclude to say that our points that we see on the map are clustered. On my slide, you can see D naught, and D naught is the formula behind the observed average nearest neighbor distances. And then the expected or the random distribution average nearest neighbor distances is what I am showing here as DE. And the N and A you see in the formulas, N is the number of points, and A is the minimum area that would enclose these points. So basically, what I explained earlier on was the comparison of these distances to see whether is D naught less than DE, or is it the other way around, so that we can conclude that we have a clustered points on the map, or we have a dispersed points. Someone can also look at it from the ratio point of view to divide D naught over DE. And once you do that, if the answer for ANN is 1, then that tells us that the points are occurring at random, because D naught on DE means those quantities are almost the same, you know. And GIS helps us to also subject this to a statistical analysis to be able to say, okay, this is the confidence level that we can say, oh, we are sure that these points are clustered or not. And that is done with these formulas at the bottom here. So we have the Z-score, which when you plot on the normal distribution of what I said earlier on for the random distribution, on my left-hand side, if you can see my mouse on the left-hand side is the results for LEP insects. And basically what this is telling us is that where you see this large area at the middle here, where they've written a caption of random, is the place where if you plot the Z-score and it fell at that side, then it means that points are occurring at random. But if it fell, looking at where it has fallen now means we can now conclude that indeed the points were clustered. And if it had fallen at this side of the distribution, then we would say the points are dispersed. Okay, and that would also apply to M. persicae insects. And looking at the two charts, we have both insects occurring, as Ethelyn mentioned earlier on. Both insects were occurring at most locations, and so they are all clustered over here. Now on this map, I kind of looked at the density of these insects for LEP and M. persicae. And on the left-hand side, the map here shows some red locations and yellow and blue locations. And what that means is that the density is basically the count over the area. And here I'm looking at the square kilometer area. And so if you look at the bottom here, where my mouse is hovering around, you see a red zone on the left-hand side for LEP. And then on the right-hand side, we don't really see red zone there, because this could be as a result of maybe sampling bias, whereby LEP was sampled a bit more than M. persicae, or it could also be as a result of these insects' resistance to certain environmental conditions. So this is the density map that I created out of these points. Then that answers the question of what is the underlying distribution. Now we know the points are clustered, and we also know that the density, how the density looks like. Then it raises another question that, okay, now that we know the spatial patterns, so what could be the underlying factors that are contributing or helping these insects to be where they are? Because like Ethelyn said, these are movable insects, but we kind of find them at one location. So here, what I did was I considered, please, can you see my slide? Sorry, let me move this. Let me move this here. Okay.
Yes,
so I considered bioclimatic variables, and I also considered remotely sensed data, that is NDVI and leaf area index. Basically, bioclimatic variables are derived factors from temperature and precipitation, and NDVI is just a quantity is an indicator for the health of plants and crops. And then also leaf area index is also an important factor that we use to quantify the growth rate of crops. And so, like Ethelyn said earlier on, that these insects, when they sit on the leaf, they do a whole lot of things and damage the leaf and suck the fluid content of the leaf and all that. That causes a lot of pressure on the leaf, and so physiological factors like processes like photosynthesis and all other phenological processes as well are unable to happen optimally. And so the crop undergoes suboptimal physiological and phenological processes. And so what I did was that I combined these factors, as you can see in this table here. I combined them, and these are the descriptions to these parameters. I combined them in a machine learning environment algorithm, which is called a random forest machine learning. And I'm going to walk you through how the random forest works. But here is basically the visualization of all the parameters. And just to show you something here, the NDVI that I used was computed on Google Earth Engine. And what Google Earth Engine does is to actually compute the near infrared and red and divide it by the normalized near infrared plus red. But the problem here is that a little bit of the map is chopped off because of some cloud mask that was at that side. And so when it does the computation, it leaves that side because of the cloud mask. But this can be fixed with a different sensor. So it's not any big deal. I just wanted to point that out so you'll be aware of that. Now, here is how random forest works, and random forest belongs to artificial intelligence. And what that means is that random forest also does what we call the regression and classification. So it is actually a supervised learning machine learning. Whenever you hear of supervised machine learning, it means that algorithm must be trained by you, the analyst, before it can work. So here I'm just presenting a graphical way of how it works so you understand. So this basket of fruits here would represent our training data, and at the bottom here you can find some decision trees and some green and orange dots. Those dots are the nodes that random forest is going to sample randomly from these baskets of fruits to determine, okay, to say, okay, based on their color, based on the size, based on the shape, I would classify this as apple. And then it does the same for another tree, and does on and on and on. It can create as many trees as, say, even more than 500 trees. When random forest is dealing with classification, it just computes, it just finds the majority voting. But when it is dealing with regression, then it will find the average of all the trees. On this map, what I wanted to introduce to the concepts behind this map is the term occurrence. In species distribution survey, the term occurrence can be either presence or absence, or true absence. What that means is that when the scientist visits the site and finds the pest or insect there, then that is termed as presence. But when the scientist visits the site and doesn't find the insect there, then that location is going to be mapped as false absence. The term true absence is very difficult to map because before you can map a location as a true absence, that means you have to visit the site multiple times, because you have to consider day and night, you have to consider season and all that, and that is very difficult to map. And so in modeling species distribution, what we do is we generate false absence data, but we make sure that the data that is generated does not fall on top of already existing presence location. So on the left-hand side is where Ethelyn sampled her data, and on the right-hand side is where we have generated the false absence data, and that is called pseudo absence. Okay, And that is for LEP, and this one is for M-Pesica. So I wouldn't go through this one again. Basically, this is the model behind the random forest. Here, I will just walk through a little bit. The model is basically looking at all the predictors, that is bioclimatic variable 1 all to bioclimatic 19. And the error factor here is because no model is 100% accurate, and so we have to factor in the errors. And that is basically the model behind this. Up here is the points, which I'm showing as some set of points here, but it's going to be overlaid on top of the environmental factors, and that gives us the prediction modeling table, which we call the regression matrix. And that is what random forest will depend on to create our maps. Random forest also gives us accuracy statistics, and so for LEP, the accuracy statistics was 66%, and for M-Pesica, the accuracy for random forest, how best random forest could understand the relationship between the occurrence, absence, and then the predictors was 59%. At the bottom, you can see A, B, C, D, and A is the list of predictors that are doing so well in the LEP prediction model. B is also a list of predictors that are able to help random forest to say, let's use this branch or let's use the other branch. And that also applies to C and D. So here I came up with this list here for LEP. Here are the top 6 predictors that I found after random forest modeling. And for M-Pesica, here are the top 6. And as you can see, it includes NDVI and LAI. In fact, LAI was the top for LEP and as well for M-Pesica. And because she said she found at multiple locations, she found these insects at the same time, I try to understand what would be the common contributing factors for that. And here, as you can see, I have Bio3, Bio19, and LAI and NDVI is repeating here as well. Bio3 is isothermality, Bio19 is precipitation, NDVI and LAI, we all know what that means already. I would walk through quickly with the remaining slides because I already spent some time off. And so the remaining slides is about how this mapping was done. And basically this graphical representation here shows us how random forest, the trained random forest is doing the prediction. So the points here signifies the locations where she did the sampling. And this is kind of a grid covering the whole of Ghana. So random forest will move to the first point and make a prediction, move to the next point until all the points over Ghana are covered. So once that is done, then it gives us the stability maps, which we can use to inform decisions. So on the left-hand side of the map is the LEP map, stability map, and on the right-hand side we have the M-Pesica. As you can see, because most of the insects were found at the multiple locations, we see similarities in the map, but like we saw earlier on, LEP were sampled at a lot of locations than M-Pesica. That is why we have a lot of greener areas here on the LEP map than compared to the M-Pesica. And like I said, the NDVI is the one that is causing this portion of the map to be chopped off, but this can be fixed using a different sensor. Here, I try to review the performance of the random forest algorithm, and I just plotted the LEP. For LEP, I plotted the leaf area index against the NDVI. And the basic understanding here is that there is a positive relationship between the two. And what that means is whenever leaf area index is increasing, NDVI is also increasing, and vice versa. If you come here, we have the suitability against the NDVI, and this is a negative relationship. The suitability is the probability to find an insect at that location. So as we find more insects at a particular location, that means the NDVI, which is recording or which is checking the health of the crop, is also reducing. So that's a negative relationship. At the bottom here, the red dots are absence locations. And at the top here, the dots you see at the top there are present locations. What that means is where we have more of the absence of the insects we see that NDVI was high at that location compared to where we have the more of the presence locations. We don't find high NDVI at that site. And comparing that to leaf area index as well, where we have a negative relationship between the suitability and leaf area index, like I said, where you have more of the presence of the insects on the leaves, the leaf area is distorted and damaged and all sort of things occur. So the leaf area reduces over there, and that also has a negative impact on the growth rate of the crop. The same thing would apply to M-PERSIC. So I will not delve into the explanation to this chart because of time, but we have similar charts occurring at both sides. Thank you very much.